Hello again, physics friends. Today we are going to talk about the double pendulum, which is a very interesting system that exhibits actually chaotic motion. Before you dive into this video, make sure that you have watched a video of a double pendulum in action. There is one linked to on the course webpage, but you can find many online. You'll notice that you can often get the bottom part of the pendulum to loop around the top part. It's a really fascinating system. So our goal today is to write down the Lagrangian for the double pendulum, and that would be the springboard for finding the equations of motion for the double pendulum. In general, the double pendulum consists of, say, one rod with a mass at the end and another rod with a mass at the end, and those rods in general would be different lengths, and the masses in general would be different masses. To simplify things a little bit, we'll assume the two lengths are the same, and we'll just call it L, and we'll also assume the masses are equal, and we'll just call them both little m, okay? And if we give ourselves, just for the convenience of the discussion, if we give ourselves a coordinate system where x is pointing to the right and y increases downwards, that will be helpful as we talk through the system, although at the end of the day we're going to use different coordinates to specify the motion. So first let's talk about how many degrees of freedom we need, right? You can kind of see there's going to be two, because you could move one pendulum, or you can move the other pendulum, or you could move both. But let's see why that is, right? So we have here two masses, which in general would require 6 coordinates, motion in x, y, and z for each of those two masses. But we have some constraints. Right. What constraints do we have? Well, first we're going to assume that the motion is in a plane. So if you'd like, the z-coordinate of mass 1 is going to be 0, and the z-coordinate of mass 2 is going to be 0. So that takes us down from 6 dimensions to 4 dimensions. We also have a constraint that mass 1 is a fixed distance from the point of attachment to the ceiling. Okay, and we can write that as x1 squared plus y1 squared is equal to a constant, L1 squared. Okay, so that brings us from 4 dimensions down to 3. And then, of course, there's one other constraint. And that other constraint tells us that mass 2 is always a fixed distance away from mass 1. We can write that down by saying x2 minus x1 quantity squared plus y2 minus y1 quantity squared is equal to the length of the second string. Okay. So now we actually have what was originally a 6-dimensional problem with two masses moving in 3D. We have these 4 constraints, and we end up with just 2 degrees of freedom. Okay. And we could draw those, so we need 2 parameters. Both of them would most conveniently be expressed as angles. There's a few ways to express those angles. Here's one of them. We could have the first angle be the angle of pendulum 1 with respect to the vertical, and angle 2 could also be the angle with respect to the vertical, but this time for mass 2. There's another way which is equivalent. It just ends up looking a little bit different, but the physics all works out just as well. You could have equivalently called one angle the angle of mass 1 relative to the vertical, and then the second angle could be the angle of mass 2 relative to the first string. Notice it's a slight difference. Either one is fine. We are going to opt for the first approach, where both angles are relative to the vertical. So our goal here is to write down the Lagrangian for the system, so we need an expression for T, and we need an expression for U, the potential energy. So a reasonable starting point here would be to write down the position vector to object 1 and the position vector to mass 2 in Cartesian coordinates. And then re-express it in terms of the angles theta 1 and theta 2. So to start, we can do the following. R1 is equal to x1, y1, the coordinates of the first mass. And same would be true for the second mass. And here I've annotated the diagram to show the x1, y1 coordinate and the x2, y2 coordinate for the two masses. And our origin x0, 0 would be the point of attachment to the ceiling. Okay, so we can see then that x1 is going to be L times the sine of theta 1, where L is the length of the string. We're assuming both strings are the same length. And y1 will be L times the cosine of that angle. For R2, we have to get all the way out here, which means we have to move x1, and then we also have to move a little bit extra, and that extra is given by L sine of theta 2. So we have to do L sine of theta 1 plus L sine of theta 2. That's the x-coordinate of mass 2, and the y-coordinate is similar, but with cosines. Okay. So we need to know not only positions, but we also need to know velocities. So let's look at the time derivatives, r1 dot. So r1 dot is going to involve derivatives of theta. Derivative of sine of theta is cosine, but we'll get a theta 1 dot in there too by the chain rule. And then we get a minus theta 1 dot sine, like so. And R2 dot, we have an overall L that we can just factor out. And inside we have theta 1 dot cosine plus theta 2 dot cosine, and then a minus theta 1 dot sine, and a minus theta 2 dot sine. So we are going to need to know velocity squared terms. So our velocity squared terms would be r1 dot dotted into itself. So that would give us an overall L squared times theta 1 dot squared cos squared theta 1 plus theta 1 dot squared sine squared theta 1. And that simplifies down to L squared theta 1 dot squared. The R2 term is a little bit more involved. R2 dot squared, rather. We have this overall L squared, and then we're going to get 4 terms, or rather 3 terms from here and 3 terms from here. So first we're going to get a theta 1 dot squared cosine squared plus theta 2 dot squared cosine squared of theta 2. And then the cross term will give us plus 2 theta 1 dot theta 2 dot cos theta 1 cos theta 2. So those 3 terms in parentheses come from the x component of our velocity, and now we have to deal with the y component. So we're going to add to that theta 1 dot squared sine squared, theta 2 dot squared sine squared, And then the cross term, which gives us 2 theta 1 dot theta 2 dot sine sine. And there we have it. Now, of course, this will simplify a fair amount. We have theta 1 squared cosine squared theta 1 dot squared sine squared. When we add those together, we end up with a theta 1 dot squared. Okay. Similarly, we have the same thing for theta 2 dot squared. Okay. And then now we have this other set of terms that involve cosine cosine and sine sine. And those we can write by factoring out the theta 1 and theta 2 dots. And we're going to see here a trig identity. When we have cosine cosine plus sine sine, that is an angle addition formula, cosine theta 1 minus theta 2. So our final step here is to say we have the square of the angular speeds plus a cross term times the cosine of the difference of the angles. Okay, so we can stitch this all together now to find the total kinetic energy, which is T1, it's 1/2 mv squared, which is r1 dot squared, plus 1/2 mv2 squared, which is r2 dot squared. So the first term, we're going to get an m over 2 L squared theta 1 dot squared. That's our kinetic energy for the first mass. And for the second mass, our kinetic energy is m over 2 L squared, and then everything in that square brackets. Like so. And we can combine this a little bit. We don't get too much more simplification beyond where we are now, but our total kinetic energy will be m L squared over 2. That's a term that's common to everything. And inside we'll have 2 factors of theta 1 dot squared, 1 factor of theta 2 dot squared, and that cross term times the cosine of the angle difference. And that's it. That's our kinetic energy. So all that's left now is to write down the potential energy, which is the sum of the potentials of masses 1 and 2, and that we can express as minus mgy1 and minus mgy2. Again, as y increases, you're going down. Going down means less potential, which is why it's minus mgy. So we can write that as minus mg times the sum of y1 and y2. But we know that y1 is L cosine theta 1, and L2, y2 has a similar expression. So we can write this as minus mg L cos theta 1 plus L cos theta 1 added to L sine, not sine, cos theta 2. So this gets simplified to minus mg, factor out that L. We have 2 cosines of theta 1 and 1 cosine of theta 2. And that is our potential. which at the end of the day now, our Lagrangian is just t minus u, and we can write that as ml squared over 2 theta 1 dot plus 1 theta 2 dot, the cross term, cosine of angle difference, minus the potential, so that's minus a negative, that gives us a plus mgl, and then we have the two cosine pieces. And that's it. That is our final expression for the Lagrangian. Now, in order to find equations of motion, our next step would then be to look at the Euler-Lagrange equation for theta 1. In other words, d dt partial L partial theta 1 dot is equal to partial L partial theta 1. And then, as separately, we want to know the Euler-Lagrange equation for the second angle, in which we take partials with respect to theta 2 and theta 2 dot. Like so. So we'd end up with two separate equations of motion. They are going to be coupled and nonlinear. So the actual equations of motion are quite complicated and not solvable analytically, but you can solve them computationally, or you can restrict yourself to small oscillations or some other set of restrictions that make the differential equations more easy to solve. But we're not going to get into that today or for this video. Instead, we're just going to close here. The goal was to practice writing down kinetic and potential energy for a multi-particle system that involved more than 1 degree of freedom, and then write down the overall Lagrangian, which we have done. So we'll stop there, but until next time, take care and be well.